Now, the next sort of question that naturally occurs is, of course, what we had before. Does t change in time? So that's the question. Does t change in time? Well, in order to answer that, we have to now take the time derivative, the rate of change of t. Okay, so let me do that. So now we are trying to calculate t dot. Well, remember that we had the following for t. We had 1 divided by e times m times p cross L minus km times r over r, the vector r divided by its length. So we have to calculate the rate of change of this thing. Okay, now let's go and do the rate of change of p cross L, the vector product of the linear and angular momenta. Okay, so vector product and the rate of change of that. What do we get? Well, we apply the Leibniz rule. So first take the rate of change of p, cross that with L, and then add to that p crossed with the rate of change of L. Of course, the rate of change of L, we know that L is conserved, so this is just 0 right there. That's the 0 vector. So this second term is actually 0. What do we get for the first term? Well, remember, p was m times velocity, and we are looking at the rate of change of that crossed with the angular momentum. So that's m times the acceleration vector, so ma. So that's the force, right? So that's going to give us the gravitational force F crossed with the angular momentum L. Now, the gravitational force has the following form, of course: minus k times m divided by r cubed times r. So if you're wondering what this r cubed is doing here instead of r squared, well, we have to divide r by its length to get a unit vector, and then have minus k times m over r squared. So that is why we have 3 copies of r in the denominator, and we have to take the vector product of this force vector with the angular momentum, that is r cross p by definition. Okay, so now let's look at this triple vector product that is r cross p. There is a nice identity, a nice vector identity expressing triple vector products such as this in a nice and somewhat simpler form. You can do the following. You take the scalar product of r and v, multiply with this number, you multiply r. So take the scalar product of r and p and multiply r by that number, and then subtract the scalar product of r and r and multiply p with that number. Okay, so did I? Oh, I made a small mistake over there. This right here should read v instead of p. Okay, and this vector here should read v as well, and there I got it right. So this vector should read v as well. So that's why I have this this m there. Okay, so what do we have now? Let's see. We have this triple product expressed as follows. So let me just rewrite this quickly. So r cross v is being expressed as this scalar product of r and r dot, basically multiplying the vector r minus the scalar product of r with itself, that's its length squared, multiplied by r dot again. Well, r dot. Yes, so you might be wondering why can I just say that the scalar product of r and v, that is r dot, as vectors gives me the product of their lengths. So for that, let me quickly say that if you take the scalar product of r with itself, which is its length squared, for this is true for any vectors, and I take the rate of change of this expression, then the equality still holds. And if you know to apply, well, here we can apply the Leibniz rule to get twice r dot r dot, the dot product of r and r dot multiplied by 2, and on the right hand side we get twice r times r dot. So this is just something called the chain rule. First we have to differentiate r squared, the function r squared, that gives us 2r, and then we have to differentiate r itself. So if we get rid of the factors of 2, we get this nice equality of the dot product of the position and velocity vectors to be the product of the distance and the speed. Okay, so now we can use this triple vector product expressed as such to be used in our next calculation. Well, to continue the calculation as follows. So what we are doing now is putting everything together and finding that the vector product of P and L, the linear and angular momenta, will have a rate of change that is k times m times minus r dot over r squared times the vector r plus 1 over r times the vector r dot. Okay, so this was obtained by looking at this calculation right here of P cross L dot. We got to this point where we had to calculate this triple vector product that we calculated to and found to be this, and then we have to take the cross product. Then we have to just put everything together. Here we have a certain scalar constant. We have to multiply that by this expression in this box, the right hand side of this box. If we do that, we'll get this expression, which is in fact nothing but km times r, the vector r, divided by its length, dotted, meaning that the rate of change of this vector. Okay, so the way you can see this, well, first you have to differentiate 1 over r to get minus 1 over r squared times r dot times the vector r, and then you have to differentiate the vector r itself, and this is how you get these two terms. Okay, so once you are at this point, you can just now go back to looking at your vector t, and you want to calculate its rate of change. Let me see if I can show you this vector. t, so we want to calculate the rate of change of this vector, but the first term was p cross L. Of course, E and M were constants, so we don't have to worry about that. But the rate of change of P cross L was exactly equal to, in the end, we found the rate of change of this other term in T. So let me just write that down. 1 over EM times P cross L minus KM multiplied by the vector r divided by its length and the rate of change of that. Okay, so this thing right here is the zero vector, because the rate of change of the first term is equal to the rate of change of the second term without the minus sign. Okay, so what we have found here is that this vector is zero. That is the rate of change of our vector t. Okay, so what we have proven, what we have proved here, is that the rate of change of t is zero. T is a conserved quantity, this vector. So that point in the circle won't move as our planet goes along its orbit. So I hope that was possible to follow. It was a bit involved, probably the most the hardest calculation of this presentation. But now I can tell you that this vector little t is conserved. So that means, that will of course mean that, let me show you here, that will of course mean that the distance between t and r and the origin is going to be constant. So this is why we get here an ellipse. Let me first tell you about t minus r, the length of t minus r, plus the length of r itself, well, from the origin. The distance of r from the origin is the length of r. So what we get here, t minus r has the same length as s minus r, because the way we got t is by reflecting through this tangent line, right? Okay, so this is why t minus r is the same thing as in length as s minus r. Okay, and to this we add r minus the zero vector. If we look at the sum of these two distances, well, you can look and you can see that this is s minus r, and this right here is r minus the origin minus the zero vector. So this in fact here is just the length of s, which is the radius, which was, if you remember, minus k over e, a constant, positive constant. Okay, so let me go back to the slides and show you that in fact what we have here is that what we have found finally is that the length, the distance of our planet from the origin and from this point t, if we take these two distances, r, the distance of r from t and the distance from r from the origin, we add these two distances up, we get a constant. We get a fixed number. And in fact, this is Kepler's first law. We have just obtained an ellipse finally. Now let me show you why is it really an ellipse. So if you look at this this notepad right here, we have two fixed points, 2 points that are fixed, and I have a piece of string which has a constant length, of course. Now I take my pen and stretch it out and start drawing so that the string is always taut. And what I'm getting here is an ellipse. So at each moment, what I have is, when I'm on the ellipse, I have these two distances from each of these points, the focus points, and when I add those two distances up, I always get the same number, which is just half the length of this string, right? So these two distances always sum to the same number. Okay, this is the definition of an ellipse, and this is how you can draw an ellipse using a piece of string and two pins. Now going back to my slides, I want us to now look at ellipses a bit and go to item pool once more. So let me go to the next question on item pool and see if you can answer this one. So the next question is about ellipses, and it says that we have a point P on the ellipse which has a semi-major axis A equals 3 and the semi-minor axis B equals 1. And the question is, what is the sum of distances of P from the two focus points F1 and F2? Okay, so again, A is that this is the semi-major axis that is equal to 3 units, and B is the semi-minor axis that is equal to 1 unit of distance. And we are looking for the sum of distances of P from the two foci. Okay, so go to please go to itempool.com/Kepler/live and do submit your answer. I will also try to look at the comments. There's not much going on, which is fine. By the way, this of course this talk is going to be recorded and it's going to be put on YouTube, so you can always look back on it. And in fact, if you are watching this after the lecture on YouTube, you can go to item pool and you can take part in these quizzes. Now let's see. Okay, so are there any? Okay, there are 2 submissions already. That's great. Okay, someone has also submitted their answer. Okay, so let me finish this poll and look at the actual answer. So there are two competing ideas there, I think. So the correct answer is, of course, 6. So, but whoever has written 2a, that's also correct. So that's twice the semi-major axis. And in fact, if we look back at the notepad, so this distance, the sum of these two distances, is always the same. So if I go all the way to this point, okay, here I have so for the sum of these two distances, fp plus f2p, what I get here is I go from this focus point, f1, I go all the way to this side of the ellipse right there, and then there's this bit, the other distance is just this bit, which is the same as this one right there. You agree that this bit and this bit are equal? So what I'm getting here is I can just take this second distance and add it over to here, and in fact cover the entire major axis that is of 2a in length of the ellipse. Okay, so right now we actually have found the semi-major axis of our planet, because if we look back in this notepad, so what we have here is we have seen that this constant for the ellipse that we have just seen to be 2a is equal to minus k over e. So in fact, the semi-major axis of our ellipse is minus k over 2e. Okay, so we have one of the axes of our ellipse, elliptical orbit, and now let's look at the other one. So let's try to figure out what the other axis should be like. So for this we have to calculate the length of t. So why do we need to calculate the length of t? Well, we know the length of a, the semi-major axis, and we know and we want to obtain the semi-minor axis. So in case we look at this configuration where this distance of 2a is given by these pieces of string as a plus a, then we have a right triangle right here with a hypotenuse a and two legs that are of a length b and t over 2. So t here is the length of our vector little t. So you can see that we could use the Pythagorean theorem to obtain little b. Okay, so little b can be obtained if we know, if we would know the length of little t. So that is the next thing we are going to calculate in this. And then we are basically finished, well, almost finished. Let me show you the calculation for the length of t. So for the length of t, what we want to calculate is we could calculate the squared length of t. So if you remember, this vector little t had the following form. It was so the squared length of t is the same thing as the scalar product of t with itself, and little t had the form. Let me go back and show you that little t was written like so: 1 over em times p cross l minus k times m times the vector r divided by its length. So I have to take, if I want to find the length of t squared, I will have to multiply this vector by itself, which is 1 over e, well, we have 1 over e times m, so in both of these factors, so 1 over e squared times m squared. Then we have to take p cross l minus k times m times r over r and multiply it by itself. Okay, so here we have the length of p cross l squared. That's just p squared times l squared, since they are perpendicular to each other. Then we have the square, well, these two vectors multiplied. That will give, this is a unit vector, so that will give us plus k squared times m squared. Then we'll have these cross terms, so multiplying p cross l with r, with the term containing r, will give us minus 2. Two of these terms have the same form, so minus 2 times k m over r times the vector r, scalar multiplied by p cross l, basically. This is how we end up with this vector. And again, here we can do a bit of rearranging to get the following. Well, the first few terms don't change, and then we have minus 2 km over r times r dot, and now p cross l is again, remember, a triple vector product, because we have p cross l cross r cross p, basically. And this can be rewritten using the triple vector product formula that we have seen before, as p squared times the vector r minus r dot p times the vector p. Okay, so this is how it can be rewritten. So what we are left with here is 1 over e squared times m squared times p squared times l squared plus k squared times m squared minus 2km divided by r. And what we have here is, well, of course, here we will get r squared times p squared from the first term when we expand this bracket, this parentheses. And from the second one, what we will get is 2, because of these two minus signs, it's going to be a plus, 2k times m over r times the length of r squared times the length of p squared times the cosine of the angle between these two vectors r and p squared. Okay, so this is just the scalar product written out in this usual geometric, using its usual geometric definition. But what you can notice here is we have 2km over r times r squared times p squared, and that again multiplied by the cosine of alpha squared. So we can use the nice trigonometric identity that is the cosine of squared plus the sine of squared of an angle is equal to 1. So we can use that to get the following. 1 over e squared times m squared multiplying p squared times l squared plus k squared times m squared minus 2km over r times r squared times p squared, and here we have minus 1 plus a cosine of squared, giving us minus a sine of squared, sine of alpha squared. Okay, so here what you can notice that this expression right here is the length of the vector product of r and p squared, and the vector product of r and p is the angular momentum, so that is the length of L squared right there. So what we get is 1 minus e squared times m squared times p squared times L squared plus k squared times m squared minus 2km divided by L times L squared. Okay, so this is what we got. Let's see if we can pull these things together. So here we have a fraction with, of course, e squared plus m squared in the denominator, and upstairs what we have here is, notice that we have L squared multiplied by p squared and multiplied by minus k over r times 2m. Okay, so it is exactly the energy multiplied by 2m what we have as the factors multiplying L squared. So this is 2m times e multiplying L squared in the brackets plus k squared plus times m squared. So this is the length of our vector t squared. Okay, so this is the length that we were looking for. So, and now we can go on to finding the semi-minor axis of our ellipse. So here's the same derivation. Feel free to pause the video if you are rewatching this and just go through it yourself. But I'm going to the next slide where we apply Pythagoras's theorem, as I explained it before, to find the semi-minor axis. So here we have the right triangle with the hypotenuse A and the legs B and T over 2, and we are looking for B, so B squared should be equal to A squared minus T half T over 2 squared. If you plug in what we have just found for the length of T, you will get that B squared is equal to L squared over minus 2em. Okay, so the two axes of the ellipse are A, which is equal to k over minus 2e, and B, which is equal to L over the square root of minus 2em. And remember, e is a negative number, so what we have under the square root is a positive expression, is a positive number. So now we have the axes of the ellipse, which means that we can in fact prove and derive Kepler's last and third law using the fact that what we have seen before is that the position vector r sweeps out an area of L over 2m each unit of time, in each unit of time, so each second, let's say. But it also sweeps out the full ellipse during the orbital period. So it means that the area that is swept out on the one hand is L over 2m times the orbital period t, but in the same time it sweeps out the area of the full ellipse, which can be written as pi times the product of the semi-major and semi-minor axes. So pi times AB. So from this you can express t as 2m times pi times a times b divided by L, and take the square of t in that expression. So if you do that, then you get 2 pi squared times m squared times a squared times b squared divided by l squared. And now you can simply plug in the expressions that we got for a and b and square those. If you do that in the numerator, and you will notice that lots of things cancel, and what you are left with is 4 pi squared times m over k multiplied by the semi-major axis cubed. And this is exactly Kepler's third law, because if now you rearrange this equality, what you get is a cubed over t squared equals k over 4 pi squared times the reciprocal of this reduced mass. Now, if you substitute everything back into this expression, so little k, we introduce little k to stand for capital G times m1 times m2. So capital G is of course the gravitational constant. M1 and M2 are the two masses that were involved in the two-body problem. And the reciprocal of the reduced mass is of course just the sum of M1 and M2 divided by the product of M1 and M2. And you can notice that the product of M1 and M2 cancels. So what we are left with is G over 4 pi squared times the sum of the masses. And if M1 is the mass of a planet and M2 is the mass of the sun, then what we have is M2 being much greater than M1. So if we add that tiny bit of M1, mass of M1 to this great mass of the sun, it's almost as if we didn't do anything. So roughly what we got for a cubed over t squared is roughly G, capital G, the gravitational constant, times the mass of the sun over 4 pi squared. And this is a constant. This would be a constant for all planets, of course. But you can see that the exact formula, so Kepler's third law, is just an approximation in the case when the sun is much more massive than its planets, which is to a good approximation is the case. So this is now Kepler's third law that we have now. And I can show you one more thing in this notebook. I prepared something that is the geosynchronous orbit, the size of the geosynchronous orbit that you need. So what you want to have is a satellite sent into orbit which goes around the Earth, and if you look up to the sky, you would see that satellite always in the same spot in the sky, because it would rotate, go around the Earth just as the Earth rotates around its axis. So it should have an orbital period of, that satellite should have an orbital period of a day. So given in seconds, it's 60 times 60 times 24. And from Kepler's third law, in which now we know what this exact constant is, it was G times the mass of the Earth over 4 pi squared. That constant multiplied by t squared and taken the cube root gives us the semi-major axis for the orbit of our satellite. And let's see what that is. Well, of course, the number of seconds in a day is 86,400, and the size of the geosynchronous orbit is 4.22 times 10 to the 7th meters. So that is something like 42,000 kilometers, if I'm not wrong. So if you look this up, the radius of the geosynchronous orbit, you will find a number that is pretty close to this number that we just got. Okay, so going back to the slides, all I have to say now is just summarizing, telling you what the moral of the story was. So you notice that this vector t played a very important, a crucial role in our derivation, and in fact, this vector t is proportional to a very famous conserved quantity in physics, which is called, denoted by capital A, and it's called the Laplace-Runge-Lenz vector. It is the worst name for such an important quantity ever, because Laplace-Runge-Lenz doesn't tell you anything about what this vector is, but it is basically an axis vector. That is why it has this letter capital A to denote it. So these, the moral of the story that conservation laws are basically very, very important and very useful. We have seen that the conservation of angular momentum led us to Kepler's second law, and the conservations of energy and the vector t led us to Kepler's first law and Kepler's third law. Okay, so this is how we used conserved physical quantities that do not change in time, to derive Kepler's 3 laws of planetary motion. Okay, so of course we could count up how many conserved quantities we found, and in fact we have this angular momentum, which is a 3-dimensional vector, so it has 3 components. Then we have the vector t, which also has 3 components, so that's already 6 numbers. And then we have the energy, which is a single number as a scalar quantity, so that's a 7th component. So we have 7 things that are conserved, but in fact only 5 of them are independent, because the vector t and so the vector a is in the plane of motion, so it's perpendicular to the angular momentum. Remember, the angular momentum was perpendicular to the plane of motion, so their scalar product has to be 0 always, and also the energy can be expressed using this Laplace-Runge-Lenz vector and the angular momentum in this way. So E can be expressed using the other 2 conserved quantities, and there is a relation between the components of A and L. So in reality we only have 5 independent conserved quantities, which is another way, well, which could also mean, what is actually true is that this Kepler problem of planetary motion is a superintegrable system. So this is just something I wanted to mention because my research is on integrable systems. And integrable systems is an area of mathematical physics where you have many of these conserved quantities, and you can use them to actually solve the equations of motion, just like we did here, and prove very useful results about your physical system that you are interested in. Okay, so as epilogue, I would say that the effect of Kepler's laws are too many to count. Of course, it gave us an accurate model of the solar system, but not quite accurate. So that's the perihelion motion of Mercury I'm referring to. So it was so accurate that indeed it took a good number of years to notice that Newton's law of universal gravitation cannot describe the motion of the planets very well to a high accuracy. So there was the motion of the Mercury. So the closest point on Mercury's orbit, when it gets closest to the Sun, is called the perihelion, and that elliptical orbit of Mercury is rotating slowly due to the effect of the other planets, the gravitational effect of the other planets. And there was a slight deviation in this perihelion motion of the Mercury. Newton's Newtonian gravity couldn't account for something like 38 arc seconds in that motion. So the way this ellipse was turning was not described accurately by Newtonian gravity, and that was only put right by Einstein's general relativity. So that is a nice sort of nice way of tying it in with general relativity. So it was accurate all the way to the innermost planet, and sort of the largest gravitational effect the sun has on a planet. Newtonian gravity was accurate all the way to that point, but then it had to be amended by Einstein's relativity. Another effect of the Kepler's laws, I would say, is in the early 20th century, Rutherford had this scattering experiment in which he bombarded a golden plate, atoms in a golden plate with electrons, and they thought that these electrons would scatter in all directions, sort of not distinguishing any direction in particular. And in fact, what they have found is that most of these electrons went straight through the atom, the plate that they bombarded with. So most of the electrons ended up on the other side of this plate, but some of them were deflected like extremely, which they explained by a new model of the atomic of the atom, in which in the very center of the atom we have a positively charged core, which not gravitationally but in a Coulomb force sort of attracts the electron and deflects it when you hit it just the right way. The atom deflects this electron via its nucleus. So that was basically, that led to the discovery to the atomic nucleus. Then there was, of course, Pauli in the early days of quantum mechanics, before even Schrödinger writing down his equation. Pauli was able to use the quantum mechanical version of these objects that we just used. So something like the Runge-Lenz vector can be understood in terms of quantum mechanics. And Pauli in 1926 was able to calculate the energy levels of the hydrogen atom. So basically using stuff that we did in a quantum mechanical setting. And that was before the Schrödinger equation. And finally, the reason, so we could of course always ask what's the reason behind all of these conservation laws being there in the Kepler problem. So why is the energy, the angular momentum, this Runge-Lenz vector, why are they all conserved? And it has to do with the hidden symmetries of the Kepler problem. So this is something that happened in much of 20th century physics, where people tried to connect conservation laws to symmetries using what's called Noether's theorem. So Emmy Noether, the German physicist and mathematician, theoretical physicist and mathematician, had this nice theorem connecting symmetries to conservation laws. And the fact that the Kepler problem has this many conservation laws hints at the fact that there are lots of hidden symmetries, and the study of symmetries in mathematics is called group theory. And this way, through the Kepler problem and the hydrogen atom, physicists started to use group theory in their work, and much of particle physics relies on these group theoretic ideas of mathematics. Okay, finally, just to finish off, I would like to go to item pool one more time and ask you how many planets are there in the solar system. Okay, so this is just for fun. Please go to itempool.com/math/Kepler/live and answer. Well, input your answer. How many planets are there in the solar system? So I would be interested to see what you think. There is of course only one correct answer when it comes to the number of known planets. There are already two answers, which is kind of fun because it means that people don't agree on the number of planets. So I'm curious to see as to what we end up with. Okay, so let me finish the poll and reveal the answer. Hopefully no one gets offended by the answer. So it's 8 planets. There are 8 planets in the solar system. So if I just go, but someone has written 7. Some people one person has written submitted 1, and that is 9. Sorry. So that person who has said it's 9 probably thought of this guy, or rather this guy. So this is of course Pluto, as was nicely captured by the New Horizons spacecraft a few years back, so there are 8 planets. Pluto has been demoted to be a dwarf planet in a good number of years ago now. So this is a cartoon version of Pluto meeting New Horizons and being very happy that it's going to it's getting a visitor, but that was a very short visit, so the cartoon is a reflection of that. Now let me before I finish, let me just say that the study of planets in the solar system is still a very active and ongoing research, and there are even ideas about a 9th planet far out in the solar system, basically outside of the Kuiper belt. There is an idea about a hypothesis about a 9th planet which would explain some of these highly elliptical orbits of objects, as I said, far outside of the Kuiper belt. And that idea actually is partially due to Mike Brown's work, who is known as Pluto Killer on Twitter. He was actually the person who was in this committee demoting Pluto to a dwarf planet from a planet, and rightly so, if I may add. This is an ongoing research. Of course, they have not found Planet 9 just yet. So let me just finish the lecture by saying that I hope that this lecture showed you how theory and experiments work together in physics. So there were observational facts and there were theoretical derivations, and by the words of Einstein, I would say, which he wrote for the occasion of the 300th anniversary of Kepler's death, it seems that the human mind has first to construct forms independently before we can find them in things. Kepler's marvelous achievement is a particularly fine example of the truth that knowledge cannot spring from experience alone, but only from the comparison of the inventions of the intellect with observed fact. So Einstein is basically saying that the ancient Greeks were studying conic sections and ellipses only for Kepler, a couple of millennia after that, to discover them in the orbits of planets. So I would like to thank you for your attention. If you followed all the way through, you deserve some sort of a prize. And if you watch this lecture on YouTube, well, after it was live streamed, thank you for your attention as well. I hope you enjoyed the lecture. I would like to ask you people to complete a feedback form, so I see what things you liked, what things you didn't. I know it was really long, this lecture, so never mind the length. Just try to give me some sort of a feedback, whether you like this format or not. I would be interested in hearing from you. So that is all I had to say. Thank you very much for your attention, and I'll see you next time.